connect to 90 centimeter is also was broken.
Good morning everyone. Today I would like to present about a land subsidence that happened near the Admiralty Proper Line construction area in Bangkok on 24 September 2025. Refer to the sinking or collapse of the ground surface due to underground soil movement or loss of support. In this case, heavy rainfall and underground water leakage caused soil erosion beneath the road surface. Happened in three stages. First, water leak into the soil. Second, the flowing water slowly washed away soil particles and create underground void. Finally, the ground could no longer support the load above it, forming a huge sinkhole. The sinkhole was about 13 meters by 4 meters with around 7,000 cubic meters of soil and water affecting nearby infrastructure including the Samsen Police Station, Bajiro Hospital, MRT construction site, nearby roads and utility system. Although no casualties were reported, many accident workers, patients and road users were affected indirectly due to the safety risks and road closure. This case shows the importance of proper underground monitoring, drainage systems, and geotechnical investigation to prevent future land subsidence incidents. I will explain the first major issue related to the land subsidence incident at Samsen Police Station in Bangkok, which is structural instability and infrastructure failure. The incident created a massive sinkhole measuring approximately 13 by 13 meters and nearly 15 meters deep near the police station and Banjira Hospital. The collapse caused severe damage to road and underground utilities, police vehicle, and nearby buildings. Engineers later discovered structural crack, little structures, and damaged foundation pile beneath the police station building. Due to this serious damage, authorities declared the building unsafe and planned for demolitions. This case is considered a common civil engineering problem because sudden large-scale land subsidence in a dense urban area is difficult to predict and can quickly become dangerous. The collapse also highlights the challenge of underground construction in weak soil conditions, especially in Bangkok where soft clay soil and groundwater-related subsidence are common issue. From a safety perspective, the incidents endangered numerous residents, road users, hospital patients, and construction workers. Authorities had to close roads, evacuate surrounding areas, and monitoring nearby structure to prevent further collapse and injury. From a social perspective, the collapse disrupted transportation, emergency service, and daily public activity in Bangkok. It also raised concerns regarding construction safety, geotechnical monitoring, and whether underground MRT construction activities, leaking pipelines, and groundwater pressure contribute to the failure. I will explain the second major issue in this case, which is environmental and urban development challenges related to the land subsidence incidents at Samsen Police Station in Bangkok. Investigations suggest that underground MRT construction activities, groundwater pressure, leaking pipelines, and Bangkok's soft clay soil contribute to the subsidence problem. Bangkok already experienced long-term land subsidence due to rapid urbanization and excessive groundwater extraction, making the engineering condition more complex and unstable. This case demonstrates how large infrastructure projects in weak soil conditions can increase environmental risk if proper geotechnical investigation and monitoring systems are not implemented effectively. Due to the continuing soil movement, authorities had to carry out emergency stabilization work using sandbag, concrete fillings, and monitoring systems to prevent further collapse and protect nearby infrastructure. From a health and society perspective, the incident affected nearby communities and hospital operation. Traffic congestion, dust, vibration, noise, and disruption to water and drainage system cause inconvenience and stress to residents and the public. Some residents also need temporary relocations for safety reasons. The incident also raised concern regarding sustainable urban development in Bangkok. Many people question whether construction projects and underground infrastructure work were properly monitored before the collapse occurred. This situation reduced public confidence in urban planning and infrastructure safety. Overall, this issue highlights the importance of sustainable urban planning, environmental management, and continuous monitoring during underground construction projects to reduce further risks and ensure safer urban development.
So next, for issue 3, we look at economic losses and infrastructure repair costs caused by land subsidence in Bangkok. As you can see, the sinking ground continuously damaged roads, bridge, drainage system, pipelines, and buildings. Because the ground keeps sinking, repairs and upgrades are needed again and again, which drives up maintenance costs. This creates long-term economic burdens for the government, business, and communities. For example, business activities and transport system get disrupted, infrastructure lifespan becomes shorter, and property values drop. Also, flooding makes the damage worse, affecting public safety, health, and even culture areas. So overall, this issue is not just about repairs. It's a complex urban challenge with wide economic and social impacts. So lastly, for issue 4, we focus on geotechnical and engineering challenges in Bangkok. The fact is, Bangkok sits on thick layers of soft compressible clay. When groundwater is extracted and buildings at heavy loads, the soil compresses and causes long-term settlement. As shown in the diagram, this process lowers groundwater levels, increases soil pressure, and leads to clay compression and land subsidence. The key problem is that Bangkok's soft marine clay settles easily under pressure. Groundwater extraction worsens this, and differential settlement makes infrastructure design and construction much more difficult. It also creates long-term uncertainty for structure performance and urban development. This leads to several impacts like buildings may crack or tilt, construction costs increase due to special foundation, settlement is hard to predict, and underground utilities are at risk. Because of this, advanced monitoring and engineering design are required. Overall, this is a complex challenge involving safety, society, health, legal, and cultural aspects, making safe and sustainable development in Bangkok more difficult.
The several cases in Bangkok highlight the consistent impact of planning conditions and ability to create the stakeholder responsibility to prevent future incidents. So these cases involve challenges expected before the fault, and addressing this problem requires strong cooperation with the authorities, ensuring this contractors developers understand the problem. So the first thing first, the insurance suppliers should continually monitor soil conditions, groundwater levels, and structural monitoring construction activities. Emergency response plans and public safety measures will also be prepared to protect the surrounding communities. So look to forget to also consistent compliance with safety procedures, since it's to ensure that potential dangers are identified early before major failures occur. Engineers also must conduct comprehensive soil investigations, assess groundwater behavior, and design suitable foundation and soil retaining system. So failure to follow engineering standards on during the geotechnical accumulation can lead to soil collapse and structural failure. So construction should comply with approved construction methods, while professional engineer must ensure all technical designs meet safety and regulatory requirements. They also need to ensure that the groundwater usage is controlled, drainage systems are properly maintained, and the environmental impact assessments are completed before the development project begins. Next, the government authorities must strictly enforce construction safety regulations, supervision permits, and geotechnical investigation requirements. It includes settlement urban planning and with environmental protection policies might help to decrease the issues. Government and construction companies should therefore invest in regular inspections, advanced monitoring technology, and perform maintenance systems. Insurance provider, utility companies, and so the local authorities should also coordinate the financial planning and risk management strategies to reduce the long-term economic impact of the cycle. And the public are advised to report warning signs as ground cracks or depressions in early stage to be alert on the future consequences. And not only that, please cooperate with the safety inspection during emergency to reduce the danger and barriers to development.
The first solution is smart underground water defense. Deep beneath Bangkok, a major water pipe burst. The escaping water washed away the soil supporting the road above, triggering a massive cave-in into an unfinished subway tunnel. The fix: proactive engineering. Instead of reacting with sandbags after a flood, future tunnels need smart, automatic waterproof doors and reinforced ships. The second a leak is detected, they instantly lock up water and mud. This stops dirt from washing away, preventing dangerous sinkholes. It also saves thousands of gallons of clean drinking water and prevents city paralyzing traffic jam. City leaders must update building codes to require these shapes, advancing UN goals for clean water and infrastructure. Stopping uncontrolled water stops the ground from collapsing. It is the single most important step to protect the public. The second solution is smart traffic and weight control. When a city's ground is already damaged, the weight of heavy traffic can trigger secondary collapse, and poorly planned detours create massive traffic jams and pollution. The fix: smart weight control. Engineers can use real-time ground sensors and laser scanners to measure the soil stability. Connected to a smart city map, this automatically redirects heavy vehicles away from the fragile zones. This will prevent further ground damage and cuts air pollution. Crucially, it keeps essential roads, like roads leading to hospital, safe and open for the environment. This real-time data gives leaders the proof they need to legally ban heavy trucks from risky streets, directly supporting the UN's goal for sustainable cities. While underground crew repairs the damage, the city above must keep moving safely. Smart traffic control is a daily necessity to prevent secondary sinkholes.
So the third solution is a sustainable material recovery and reconstruction framework, where the aftermath of the sinkhole requires a rapid demolition. Thus, engineering solution is the Green Urban Deconstruction Framework, which prioritizes the controlled dismantling and maximum recycling of the structural materials over rapid demolition. So since immediate reaction is required, rapid demolition is very costly and expensive. So this framework prioritizes of the on-site processing of residual waste and material instead of disposing it to landfills. So using machinery such as mobile crushers, we can process the residual waste into recycled materials such as recycled aggregates. This fully utilizing the materials can also ultimately reduce the cost. Utilize the recycled materials can also reduce the cost for new raw materials. So what are the impacts of this solution? To society, it prevents displacement and also disruptions of the local community. So a research by Akabas and ECC in 2025, they have studied that the benefits in utilizing on-site materials can conclude that it reduces the transportation of new materials and also reduce noise pollution and traffic congestion. In terms of environmental, they have also studied that the idea is to reuse salvage material as recycled concrete aggregates have shown that it leads to a reduction in carbon emissions of processing new raw materials. Thus, this reduces environmental impact by minimizing landfill waste and also reducing the carbon footprint of the processing of new materials. So in terms of safety, the construction process is much more safer than demolition as it involves a controlled dismantling and also uses digital technology. So MRT Purple Tunnel, the construction requires careful procedures to prevent from the further structural failure in the tunnel system. And lastly, in terms of the regulatory, so we must align it with both the local municipal codes and also engineering standards, in which that the recycled material must be tested first with the Department of Rural Roads (DRR) and also Department of Highways (DOH). This is to ensure that the materials have adequate structural quality. So in terms of the SDG alignment, this solution is aligned with the SDG 12, Responsible Consumption and Production, and also SDG 11, Sustainable Cities and Communities, as we adopt a sustainable solution for the materials recycling and integrate it with a deconstruction process. So the fourth solution is a ground monitoring framework and integration of advanced soil stabilizations. So due to the Bangkok area is underlain by thick layers of soft marine clay, combined with the groundwater extraction and also urban loading, it leads to a long-term consolidation settlement and structural instability. So the engineering solution that we have proposed is a real-time monitoring and utilizing advanced soil stabilization techniques such as deep cement mixing and also dead drafting. So real-time monitoring, it uses settlement gauges such as inclinometer, geoforms, and also networks such as INSAR. So this is to detect any early potential ground failure and measures the ground deformation, subsurface tilting, and also ground vibrations. So deep cement mixing is to accelerate the consolidation and increase the shear strength of the soft marine clay before the deconstruction process of the MRT tunnel. So this can be proven by a research by Zuzek in 2024, where they have concluded that this DCM is very suitable for large construction site with soft clay soil and cost effective to reduce settlement. So for the jet grouting, it is to provide immediate reinforcement during deep excavations of the MRT tunnel by replacing a portion of a soft clay with the rigid grout columns and increase the shear strength of the soil. So the impact of this solution to society, it prevents ground failures. So it prevents and avoid cracks and also tilting of the buildings, the residential buildings and the heritage sites. Thus, it ensures a long-term community continuity of the society and the surrounding area. So for environmental, through ground monitoring, it reduces the risk of sewer and pipeline ruptures, hence preventing the contamination of both soil and also water. Soil stabilization can prevent soil compression and also reduce the rate of settlement. So in terms of safety, the advanced geotechnical monitoring and also modeling, it prevents settlement and act as an early system warning, and also for infrastructure protection, ensuring the safety of underground utilities, facilities and transport systems such as the MRT tunnel. So for the regulatory, engineers must have a legal and professional duty to adhere to updated subsidence codes such as the Engineering Institute of Thailand, EIT standard, and also Building Control Act 1979, as this case is in Thailand. So this is to avoid any liability for the infrastructure failure. So for the alignment of SDG, adopting an advanced technology to solve the issues such as ground monitoring and the advanced soil stabilization techniques are aligned with the SDG 9 and SDG 11.